For a really long time, individuals have imagined what life may be like in other universes. Thanks to the James Webb Space Telescope, the most advanced telescope in existence, that question may finally be able to be examined. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed a couple of specific anomalies from one of the planets in the system, Proxima B. These irregularities, called artificial lights, have shocked some of the best minds in mainstream science. But what are they? Do these lights suggest the presence of intelligent life on the planet? Join us as we investigate the James Webb Space Telescope's disturbing discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To conduct such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The nonprofit's objective was to assemble spaceborne radio transmissions. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the extraordinary Allen Telescope Array in the California Sierra Nevada mountains. However, in the past 30 years, no definitive extraterrestrial signal has been found. Following that, the James Webb Space Telescope's successful launch boosted the mission to examine a range of distant planets revolving around other stars. As the largest telescope in the world, floating about 1 million miles from Earth and equipped with incredibly sensitive detectors, it has the potential to uncover groundbreaking discoveries. A long time ago, there were no known planets outside our solar system. However, since then, more than 4,000 exoplanets have been found orbiting various stars. According to NASA, the universe might contain trillions of exoplanets. Early signs of something happening beyond our solar system may be seen in extraterrestrial vegetation. The Galileo spacecraft, on its course to Jupiter, turned its instruments back toward Earth and detected a clear indication of plant life by recognizing the vegetation red edge, a biosignature that consists of a mix of red and infrared light reflected by plants. For example, a planet like Earth covered in a jungle should have a strong and easily noticeable red edge signal. The James Webb Space Telescope, JWST, will measure the red edge of distant, Earth-like planets in the habitable zone around stars, which could provide significant clues about what's happening beneath the surface of an exoplanet's atmosphere. When sunlight crosses a planet's star, the JWST could potentially detect it as it enters the planet's atmosphere. The missing frequencies would then be viewed through spectroscopy as particles and molecules in the atmosphere absorb specific frequencies, creating a unique fingerprint that the JWST can recognize. This technique may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, made of a combination of oxygen, nitrogen, and carbon dioxide. By looking for components that aren't commonly present, we may be able to detect intelligent life. For instance, chlorofluorocarbons, CFCs, chemicals created for use in refrigeration and cleaning products, would likely be detectable by extraterrestrials observing Earth's atmosphere from afar. If the JWST finds CFCs in planetary atmospheres, it would be a definitive sign of technological civilization. However, life on exoplanets may not resemble life on Earth at all. Sometimes even regular living things like extremophiles, species that can survive in conditions where other life forms would die, may appear extraterrestrial. These organisms, mostly microorganisms, can endure extreme conditions, such as temperatures up to 250 degrees Fahrenheit or strong acids with pH levels under 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it may be wise to focus first on those prime candidates. These planets could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is classified as a yellow G-type star, which is rarer and generally has shorter lifespans. However, in our galaxy, the likelihood of studying planets orbiting red dwarf stars, more common stars with lower luminosities and temperatures than the Sun, is higher. This longer time span allows for the development of life and evolution to produce complex organisms. Around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller size and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to that of Earth's Sun. Due to the close orbit of its planets, the clearest opportunity for us to see city lights outside our solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is many times dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun in order to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in Proxima Centauri's habitable zone, a Goldilocks zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri. However, it is possible that Proxima B is an airless, dormant planet. Considering that it orbits its red dwarf star at a distance of only 4.6 million miles, this close orbit exposes it to intense solar winds that could strip away its atmosphere. Nonetheless, Proxima B receives enough sunlight for temperatures and liquid water similar to Earth. Due to its proximity to its star, Proxima B is thought to be tidally locked, always showing the same side to the star, just like the Moon does with Earth. Proxima Centauri is about 18% the mass of the Sun and emits significantly less light, only 5% of the Sun's brightness. It may seem like a scorched, barren planet. However, liquid water could exist on Proxima B, as long as the planet has an atmosphere to retain heat. Since the total energy reaching it from the Sun is only 65% of what Earth receives, the planet may not be especially hospitable to life, but it remains the best candidate. Since it's tidally locked, Proxima B always faces the same side toward the star, resulting in permanent daylight and night with extreme temperature variations. Proxima B also receives nearly 4 times the amount of high-energy radiation that Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded by high-energy particles during solar flares. Unless it has a protective magnetic field like Earth's, the conditions for life may not be ideal. Still, suitable conditions could potentially make Proxima B a more inviting world. Unfortunately, models suggest that the atmospheres of tidally locked planets may be prone to rapid breakdown due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be renewed by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we don't know anything about Proxima B's volcanic activity or magnetic field strength, we can't accurately estimate whether the planet has an atmosphere. However, since an atmosphere suggests the presence of seas, and both together suggest the presence of life, there is great anticipation to find out whether Proxima B has a complex biosphere. It could have solar power charging stations covering the day side to produce energy, lighting, and warming the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has sparked a rush to determine if it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, enabling them to estimate its density and confirm its rocky composition, giving clues about the materials that make up its surface. During a transit, starlight could pass through the planet's atmosphere. However, the likelihood that the orbit will be in the right alignment for scientists to observe a transit is only 1.5%. The star's tendency to flare complicates matters. Astronomer David Kipping of Columbia University states that the star is unstable, as solar flares cause a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a specific type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was specifically designed to detect infrared light. Proxima B's infrared signature is key to identifying the planet's atmosphere. Furthermore, the infrared capabilities of the JWST are far superior to Hubble's, which could allow it to detect city lights on Proxima B's night side, even if they are as faint as those used on Earth. The JWST could detect artificial lighting, provided it is limited to a frequency band much smaller than the star's light. Proxima B's day side may be heavily covered with solar panels reflecting starlight. As Proxima B orbits its star, it faces a constant pattern of day and night with extreme temperature variations. The temperature contrast between day and night will depend on whether the planet is completely made of exposed rock. If it lacks an atmosphere, Proxima B's dayside and nightside temperatures will vary greatly, since the dayside will radiate all the energy it gets from Proxima Centauri as a black body. We can calculate the exact amount of black body radiation that should be present. The night side, on the other hand, would resemble a frozen wasteland. If the temperature contrast between day and night is less pronounced, we can infer the presence of an atmosphere. We'll only take the JWST 11.2 Earth days to measure the infrared radiation from Proxima B's two sides after it has completed its orbit around the star. If Proxima B has an atmosphere, the next step will be to analyze its composition. The presence of gases like oxygen, water vapor, and methane could indicate habitable conditions, if not actual living organisms. However, to achieve this, we need to effectively capture starlight as it passes through or reflects off the planet's atmosphere, which is an extremely difficult task. The JWST can closely examine some of the closest potentially habitable worlds, but it was not designed to explicitly search for extraterrestrial life. It is limited to monitoring changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. The JWST cannot detect the presence of free oxygen, which is the strongest evidence of life, even though some combinations of these gases may suggest life. One of the planned ground-based observatories that will be able to conduct a more detailed atmospheric examination is the Extremely Large Telescope, which is expected to begin operations in the 2020s. Ozone may be among the substances the JWST will be able to detect. Until those telescopes are operational, the JWST may provide data that we can consider for the next 10 years. Furthermore, more advanced space telescopes may use cutting-edge techniques to block out the blinding light of a planet's host star, revealing starlight reflected back from the planet, like covering a light with your hand to improve your ability to see distant objects. Future space telescopes may achieve this by using small internal covers or large external umbrella-shaped satellites. Once starlight is blocked, focusing on light shimmering off a planet becomes much easier. Unfortunately, most of the gases produced by Earth's life forms can also be created by non-biological processes. For example, methane is a gas produced both by cows and by volcanic springs, and sunlight can convert water molecules into oxygen and hydrogen through photosynthesis. While searching for extraterrestrial life, astronomers are sure to encounter some false positives as a result. Space researchers need a thorough understanding of a planet's conditions to assess whether its geological or atmospheric processes could resemble a biomarker, helping to rule out false positives. The next wave of planetary exploration may yield the definitive proof needed to establish the truth of life beyond Earth. The James Webb Space Telescope's groundbreaking data offers us a glimpse into the monumental changes to come. If there is life elsewhere in the universe, it addresses one of science's most pressing questions. Is it possible that life is abundant throughout the universe? Or might we be completely alone, limited to a single planet in deep space? Regardless, significant philosophical or existential shifts among humanity will likely be necessary for the eventual resolution of this journey. The search for extraterrestrial life has fascinated humankind for centuries, sparking countless stories and hypotheses. As we advance technologically, our understanding of the universe expands, revealing more opportunities for life beyond Earth. The use of space telescopes like the James Webb not only enhances our ability to detect distant planets, but also allows for detailed analysis of their atmospheres, helping researchers identify potential biosignatures. Additionally, the study of exoplanets fosters collaboration among globally established scientists and international space research organizations, advancing knowledge sharing and resource pooling, thereby increasing the likelihood of significant discoveries. These cooperative efforts also heighten public interest and engagement in space exploration, as discoveries are often shared with a wide audience, sparking curiosity and imagination. Ultimately, the philosophical implications of finding life elsewhere will prompt profound reflections on our world. With the discovery of extraterrestrial civilizations, our understanding of life's purpose would change. Such questions challenge us to rethink our role in the universe and our relationship with our home planet. As we continue to refine our techniques and methods for exploring the stars, each new discovery brings us closer to answering the age-old question: Are we alone in the universe? The journey ahead is full of potential, driving the quest for knowledge and understanding beyond our natural limits. As the James Webb Space Telescope, JWST, continues to gather unprecedented data from distant star systems, scientists are beginning to uncover details about the nature of exoplanets that could revolutionize our understanding of life beyond Earth. One of the most exciting aspects of the JWST's potential is its ability to detect not just the composition of a planet's atmosphere, but also the subtle signatures that might indicate the presence of biological or technological activity. This includes looking for gases that are typically associated with life processes such as methane, oxygen, and nitrous oxide, or even more specific markers of industrialization, like CFCs or pollutants that would not be present in the absence of advanced civilizations. Such discoveries could be groundbreaking, providing the first definitive proof of life beyond Earth. Additionally, the detection of artificial light from distant exoplanets, as suggested in some of the observations of Proxima B, opens up entirely new possibilities for space exploration. If future observations confirm that cities or even small settlements are lighting up these distant worlds, the implications for humanity's understanding of its place in the universe would be profound. The discovery of such technology would not only signify the presence of intelligent life, but could also offer insights into how extraterrestrial civilizations have developed. Are they thriving in ways similar to our own societies, or have they faced challenges that we are yet to comprehend? As our technology improves and our telescopes become more sensitive, it is also possible that we will identify even more subtle indicators of extraterrestrial civilizations, such as the traces of large-scale engineering projects or artificial modifications to a planet's environment. These could include megastructures like Dyson spheres, or even evidence of large-scale spacefaring civilizations capable of altering their planets on a planetary scale. Such discoveries would raise questions about the nature of technological evolution and whether civilizations reach a point where they are capable of transforming their environments to suit their needs. In the coming decades, we can expect to see many more exciting developments in the search for extraterrestrial life. As international space agencies continue to collaborate on ambitious missions, the quest for knowledge about the cosmos will only intensify, providing humanity with even more tools to investigate the possibility that we are not alone in the universe. This journey is not just about discovering alien life. It is about redefining our place in the cosmos and seeking answers to some of the most profound questions humanity has ever asked.